Thank you so much for the intro. Yeah, so I'm Aaron Turon. I'm an employee at Mozilla Research, and I'm really excited to tell you about our Rust project, which is, been an ongoing research project for the last sort of 4 or 5 years in terms of having a lot of manpower behind it, and is just on the cusp of actually being introduced in 1.0 sort of to the world to use as a more serious product. So my background is in programming languages. I did research in programming languages, and it's kind of an interesting time to be a person working in programming languages because for a long time it had been considered a sort of dead area. Everybody was happy with C or Java or what have you, but in the last few years there's been this kind of resurgence of interest in new programming languages with lots of different industry groups coming out with languages, including Facebook and of course Mozilla. So with all these languages coming out, you might ask, okay, what is sort of special about Rust? Why Rust? Why is Mozilla building Rust? So the kind of headline for Rust is safe systems programming. I'm going to explain what I mean by that in the next few slides. But in terms of sort of the lineage going into Rust, you have traditional systems programming languages like C and C++, which I'm sure all of you are familiar with. And then languages that might be a little less familiar, like ML and Haskell. Actually, I'm curious, who in the room is familiar with either of those languages? OK, so quite a few people. That's great. So Rust is sort of trying to blend the best of both of these languages to get at this problem of safe systems programming. What's that?
By avoiding the bugs?
Yes, exactly. OK, so one question you might wonder is, why is Mozilla interested in creating a programming language? So probably all of you know that Mozilla is the organization that created the Firefox web browser, which is currently written in C++. And it turns out, actually, that web browsers have a sort of need for a combination of things that are in deep tension. So on the one hand, web browsers need a high degree of control over the machine. They're sort of asked to do very complex tasks very quickly. They're asked to display media. They're asked to have all of these tabs running simultaneously, running code that's untrusted, that's been downloaded from the internet. And then on the other hand, they need safety because they're running this untrusted code from the internet, right? And everybody's out there trying to break into your machine. And these two are sort of at odds because languages like C and C++ that give you the kind of control you need to get the performance for a competitive browser also leave you open to all kinds of security vulnerabilities, right? And so you're constantly hearing this, Firefox has been patched or Chrome has been patched. Somebody can break into your machine through a website. So the idea is we want to build the next generation web browser, which is a project called Servo. And we want to do it in a new language that tries to do better at giving you safety and control at the same time. And so Rust and Servo are kind of this symbiotic pair of research projects. OK, so that's the really high-level picture. Now, I want to spend a little bit of time going into more detail about exactly what I mean by control and what I mean by safety. So let's start with control. So C++ is sort of the best existing language in this respect. And even in just a small snippet of code, we can start to see the kind of control that you get over the machine. So for example, if we declare a vector in C++, we know exactly how that's going to be laid out in terms of the memory. So in particular, there are some fields of the vector, including a pointer to the actual data and some metadata about it, that all live on the stack. And it's very important that that data is allocated on the stack. And then there's a pointer that goes directly to the heap. And in this particular case, we have a vector that's containing a string. And we sort of have the same pattern again, where the string is itself another vector. And the relevant sort of pointer and metadata is stored in line in the array. So to actually get at a piece of string data, you follow these two indirections. One to get into the vector itself on the heap, and then one more to get into the string. And we'll contrast that with some other languages in a second. But the high-level point here is you know exactly what things are going to look like in memory, and you have a lot of control over that layout. In addition, C++ gives you various kinds of pointers, including things like these lightweight references, which can point into the heap and they can point into the stack. And there's no overhead for doing so. You have sort of all of the power you're normally used to with pointers. And then finally, there's something implicit here, which if you know C++ is sort of obvious. So at the end of this function, the vector goes out of scope. And as a result, its destructor is run and its memory is freed. You didn't have to say anything for that to happen, so that's a nice convenience. But on the other hand, you know exactly when it's going to happen by reasoning about the scope. So that's in contrast to something like garbage collection, where the data might be freed at some point in the future, but you don't know exactly when, you can't control it, it might be inconvenient. OK. One of the principles that you get out of C++ is something often called zero-cost abstraction. And what this means is that you can build up libraries like vectors and strings that are reasonably convenient to use. They give you a nice abstraction. But when you compile it down, it's nothing different than something you could have written by hand in assembly. You're sort of not giving up any performance in doing this. OK. Now, if you look at a language that is safe but doesn't give you control, like Java, the story is very different. So in Java, if we tried to sort of set up the same scenario where we have a vector containing strings, we have layers and layers of indirection because Java enforces a kind of uniform representation on everything. It doesn't give you control over stack layout versus heap layout and so on and so forth. Right? And so in Java, any abstraction comes at a cost. And I want to be clear here. I've been focusing on memory layout as a relatively simple example, but this applies to many, many things. So being able to choose between static dispatch and dynamic dispatch. Again, in Java, basically everything is dynamically dispatched. Everything is going through objects. In C++, you have the choice. Template expansion is related to that, and there are many more examples. So what we want is to retain this notion of zero-cost abstractions and control from C++, but to somehow get the kind of safety that languages like Java, ML, Haskell, and so on provide. OK, so now what do I mean by safety? So let's go back to this example in C++, where we've set up a vector. We have a pointer into that vector. And let's just say, for the sake of argument, the vector has one element and a capacity of 1 right now. If we then try to push an element onto the vector, well, it's out of capacity. So it's going to have to allocate a new chunk of memory and copy over the data. And at that point, it'll swing the data pointer right to that new location on the heap. Problem is, we're left here with the existing reference, elem, to the old location on the heap, right, that hasn't been updated. So this is the classic dangling pointer problem. And of course, if you then go on to dereference that pointer, bad things can happen. People can break into your machine, right? This is the source of security exploits, like a very simple example. OK. So I want to sort of take a closer look at exactly what went wrong here. What are the ingredients we need to create this kind of security problem? So basically, I want to say we need two things happening at the same time. One of them is aliasing. That is, we have two pointers to the same, or multiple pointers to the same memory location. Right? So we had the data pointer, which was being updated, and then this elem pointer, which sort of didn't know about the update that happened. So aliasing is one thing, and then mutation is the other. Right? If you weren't allowed to change the data, then this problem wouldn't happen. So it's this combination of having multiple pointers and being able to change the data under those pointers that can cause things to get out of sync, and then you can read unallocated memory. Okay. And by the way, please ask questions throughout. Are there any questions up to this point? Yeah.
What architectures right now have you implemented your language on?
So the Rust uses LLVM as a backend. So basically, it supports all of the architectures that LLVM does. On the other hand, that's the in-principle answer. There's a lot of work to make different things like the standard library work on those architectures. But we work on x86 machines. We work on ARM, Power, and a few others. I mean, it's mostly major architectures at this point. Yeah.
So how much do you depend on the safety of LVM? LVM makes transformations on the abstract syntax tree and eventually walks to generate code.
Yeah.
Produces various optimizations. It makes assumptions about the safety of those transformations.
Right. So that's a really great question. One interesting thing about targeting LLVM is that we inherit a lot from C and C++ because that's sort of where LLVM is targeted. And as we'll see later in the talk, in C and C++, there's this notion of undefined behavior, something like dereferencing a pointer like this. And part of the idea of undefined behavior is it's a contract between you and the compiler. If you do something like this, the compiler is free to optimize it in crazy ways. I mean, basically, you have no guarantees about the semantics of your program, right? On the other hand, if you don't have undefined behavior, everything is supposed to work out hunky-dory, right? And so part of the idea with Rust is that it gives you a lot of tools where basically if you follow the discipline I'll be showing you in Rust, and the compiler enforces that, then you never introduce undefined behavior, right? It's only if you sort of break out of the rules.
You haven't mentioned anything about multi-threading and the problems that will come from that.
Right, so I'll spend about half of the talk talking about concurrency. Any other questions? All right. So one thing you might be wondering is, doesn't garbage collection solve certainly the safety problem? Well, as I sort of already mentioned, garbage collection gives up a lot of control. In particular, you lose that deterministic destruction where resources are freed. And it also requires a runtime, which is a sort of substantial abstraction penalty that you're paying. But there's sort of a more interesting reason that garbage collection isn't the whole answer here, which is that garbage collection solves a certain category of problems, like memory safety problems, like the dangling pointer problem I showed you. But there are many other classes of bugs that garbage collection doesn't give you any help with, such as iterator invalidation, where you have a piece of code that's iterating over some data structure and makes a call that updates that data structure, therefore sort of invalidating the iterator. Right? Garbage collection is completely orthogonal to that. And there's also something called data races, which come up with concurrency, and I'll spend a while talking about that later. So I just want to say garbage collection is, even if you're willing to give up some control, it still doesn't solve all the problems you might want to solve. But Rust will actually help you with all of these problems. OK, so that's the problem space. Those are the goals. So what is Rust? So at heart, Rust is about ownership. There's a discipline built deep into the type system that enforces a notion of ownership and a sort of related notion of borrowing. So the idea is that every resource in the language always has an owner at all times. And by resource, I mean things like a vector, but I also mean things like a file or a log. It can mean a wide variety of things. Once you have some resource, you can lend it out on a sort of temporary basis. That's what we call borrowing. And when a resource is borrowed, then certain restrictions apply. So for example, it might not be mutable, or it certainly can't be freed until the owner actually says, I'm done with the object. Okay, that's ownership at a very high level. I'm going to be explaining this at sort of increasing levels of detail, but that's the core solution. So sort of in graphical form, how does this help? Well, basically, it solves all of the problems that I've mentioned. You don't need a runtime to follow this discipline. It's totally done at compile time in the type system. So that puts you sort of in the ballpark of a language like C++, giving you the control that you wanted. You get memory safety, which was one of the benefits of garbage collection. But then you also get data race freedom, which there aren't really mainstream techniques that give you that kind of guarantee. And again, I'll come back and explain exactly what I mean by data race freedom, but it has to do with concurrency bugs. OK, and then I just want to briefly say, I'm going to spend the rest of the talk basically focusing on this notion of ownership and borrowing, because that is really the heart of Rust. But the fact that Rust is as successful as it has been, sort of as an early project, has to do with a lot of other things as well. So Rust feels like a very modern language. It borrows a lot of ideas from languages like ML and Haskell that make it feel very nice to program in, despite the fact that you're sort of dealing at this low level of abstraction and exercising this kind of control. And then finally, I just have to give credit to the open source community around Rust. I introduced this slide both to give credit, but also to invite all of you to join this community. It's very open, very welcoming. If you're interested in this stuff, it's very easy to get plugged in. OK, so now let's actually dive into some of the details. So I'm going to start by talking about the core concept of ownership, which is very simple, and then we'll move on to borrowing. Okay, so at the stick figure level, imagine you have some resource like a book. So as I said, these resources always have a clear owner at all times. So right now we have an owner on the left. Ownership can be transferred to a different party. And at that point, the original owner is irrelevant. So you can think of owners here as threads. You can think of them as functions, pieces of code. But basically, ownership transfer makes the original owner irrelevant. And when the final owner says, I'm done with this resource, the resource is destroyed. In the same way that we saw the vector example before, the destructor is run. So it's only when the final owner just drops it on the floor that the destructor is run, just like it is in C++. Okay. That's it, very, very simple discipline. So in terms of, remember we looked at this problem of memory unsafety and said you sort of need these two things, aliasing and mutation at the same time to cause this problem. So ownership chooses basically to forbid aliasing. There's always exactly one owner. There's basically only one alias that can be used at any time for an owned resource. But the owner can do anything they like to the object, so they can certainly mutate it. Okay, that's the stick figure version. Now let's see the same thing with some code. Oh, yeah, question?
Ownership is a property that exists only in compile time.
Yes.
And so, is it true that there are not algorithms where ownership is mutable and usable at execution time? And then you actually have a representation for things of data type ownership.
Right. Again, great question that you keep sort of looking forward ahead to some stuff I'll cover later in the talk. So yes, I mean, so certainly this basic ownership discipline, before we get to borrowing, is way too restrictive to write many algorithms. It's actually surprising, it gets you surprisingly far for programming applications that just use libraries of existing data structures and so on. But if you wanted to implement a doubly linked list, you'd be in trouble with this approach, right? And that's a pretty core data structure. So I'm going to come back to this point. There are various ways to bend the rules, but it's all carefully encapsulated. Other questions before we move on? Okay, so I want to come back. Now this is an example. Now we're looking at Rust, but it's sort of similar to what we saw with C++ earlier. So we introduce a vector. It's laid out on the stack exactly as it was in C++. When we create the vector, it's owned by this piece of code on the left. So that owner can go ahead and mutate it. It can push elements onto the vector. That's totally fine. And then at some point, it can pass that vector to another function. And notice this function take is just writing the type vec directly. No sort of incantations or anything else. By default, if you just write a plain type, what you're saying is that when you pass me this argument, you are actually passing ownership of that value. Okay, so this borrowing stuff is something you will annotate, as we'll see later. But by default, if you don't say anything else, you're transferring ownership. And so that means after this function call to take, the original function give no longer has ownership of the vector. Basically, it's completely irrelevant. Okay, and in terms of what this actually looks like sort of at runtime, when you make the call, right, you're going to copy the stack data into the stack frame of take. And then at that point, the original stack data is still there, but it's sort of unusable. And the type system is going to enforce that, as we'll see in a second. Then take executes. And here's a key point. If take didn't pass ownership of vector somewhere else, we're back into the same situation we saw with the original C++ code. At the end, it's going to free the vector. And so now you have what looks like a dangling pointer here, but it's grayed out. Okay, and I'll show you what that means at the compiler level. Right. So you might worry, what's to prevent give now from going on and using this vector, which has been deallocated? So this is where the type system actually comes in and does some checking for you. The type system understands that you've transferred ownership of the vector after this call, And so if you then try to use the vector in any way, say by pushing more elements, you'll get a compile error that says, this vector has been moved. You don't own it anymore. You don't have access to it. So even though there's a dangling pointer in the stack frame, it's not usable, so it's not causing any trouble. Right? That's kind of the point here. And eventually that stack frame will be popped, of course. Okay, and this kind of checking certainly covers basic errors like use after free, as we just saw, or double moves where you're claiming to transfer ownership to multiple places. And we'll see some more examples of other things that it addresses later on. But any questions about just the basic ownership discipline? Yeah.
Do standard type like int and everything also are moved this way?
Good question. So there's a notion of what we call copy types. So scalar values like integers are considered copy. And what that means is that when you do something like this function call, where it looks like you're moving ownership, you still retain access to the original value, because basically you're saying that you've just copied the value when passing it in some sense. And in particular, so the compiler checks whether copy is a valid thing to apply to a type, and you can't use it for types that involve the heap in any way. So it's always shallow scalar types. But yeah, if you had to follow this discipline for just basic programming with integers, you'd be in trouble. Integers are not resources, right? They're just values that you can easily copy around. Anything else? Okay. So now let's look at the other aspect of the ownership system, which is borrowing. Now there are two forms of borrowing in Rust, and we'll look at both of them in turn. So the first is what we call shared borrowing. And it's a little hard to imagine the right physical metaphor here. But it's as if the original owner is able to simultaneously give access to a resource to some shared group of other parties. And for that to solve the safety problems, of course, we've created aliasing, therefore we must rule out mutation while this is happening. Right? So you can share pointers to this thing with all of your friends, but none of them are allowed to actually mutate the data through their aliases. Okay. Then, in contrast, there's also a notion of mutable borrowing. And in this case, you're sort of lending it out to one party who could, for example, subsequently lend it out to another party. But there's still only one borrower active at a time. Right? So here we're ruling out the aliasing, but allowing mutation. And unlike the ownership transfer situation I described before, the original owner is sort of still important here. There's a stack discipline, basically, where ownership is getting returned from party to party until it goes back to the original owner. Okay. Right, and as I said, this approach prevents aliasing and allows mutation. Okay, so that's the stick figure version. Here's the code version. I'll start with shared borrowing. Okay, so the code on the left is pretty similar to what we saw before. Really, the only difference is that there's now this ampersand in front of the vec, and the code on the right has an ampersand in front of the type. All right, and that, as we saw in the previous slide, that designates a shared borrow. All right, so initially the code on the left owns the vector. It can mutate the vector, pushing some contents, and then it hands out a borrow of the vector to the code on the right, or a shared reference. What this looks like at runtime is a little different than what we saw before, because these references are just pointers. Right, so this is also referenced in this sort of C++ sense. Okay, and then the function on the right can do whatever it does, but unlike the case we saw before, when it finishes, right, it's relinquishing ownership not of the vector, but of the borrow. It's saying basically the loan has expired. And so that pops the reference off the stack, but the original vector is still available. And that means that the original code could go on to mutate it or transfer ownership or do whatever else. Okay. Now remember, I said for this to actually solve the safety problems, you can't allow mutation while this is going on. So there are certain things you won't be allowed to write in the function, in the use function, right? You can't push things onto the vector. You can't mutate the contents of the vector. Basically, it's a frozen object from your perspective. You can read from it, but you cannot modify it in any way. And that's all, again, enforced at compile time by Rust's type system. Okay, and I'll put an asterisk here because you, as I said, you can bend the rules in various ways. We'll see that a little bit more later. Okay, so that was shared references, shared borrowing. Here's an example with mutable references. So this is a function that's just pushing all the contents of one vector onto another. So the source vector is taken as an immutable borrow because it doesn't need to be updated, and the target vector is taken as a mutable borrow. And then internally, you are allowed, to call mutable methods like push on the target vector because it's a mutable borrow. And I'm going to skip the details here, but basically, although you're writing this for loop at what seems like a high level using these iterators and so on, it compiles down to the same kind of code that C++ gives you. So there's some zero cost abstraction going on here, but that's not super important. Right. So in terms of what's going on in the layout, as you're iterating over this vector, you're getting references onto the heap in the form of this elem, and then you're pushing copies of those references over onto the other vector. Okay, now here's an interesting question. One thing that can go wrong with this kind of code is if you happen to pass the same vector as source and destination. All right, let's step through and see exactly what happens. So suppose we've started the loop, right? We have an elem pointer like this, and the next thing we're going to do is push that onto the vector. But now we have the same kind of problem we had before. If the vector is out of capacity, that's going to involve allocating some new memory and copying over the contents. And now we have a dangling pointer again, right? And so if we continue iterating, we're going to try to read a dangling pointer. We're going to have the same kind of safety violation.
The parameters are by value or by reference?
They are
something else.
They are by value, but a parameter like this is taking a reference, right? So it's a little hard to answer that question, I guess.
Yes.
So you can think of it as by value, but then you have reference types, right? Yeah. Yeah. Okay, so it would be bad if Rust allowed this, but it doesn't. So how is this ruled out? Well, we have this function signature, right, that says it's taking, on the one hand, a shared borrow of a vector, and on the other hand, a mutable borrow of a vector, right? And then at the call site, we're taking this borrow, right? Ampersand you can think of as a sort of request alone, right? Request to borrow this value. And the problem is that we can't have both of these borrows simultaneously. So Rust is actually tracking which values have been borrowed in what way. And it can see that you're trying to borrow the same vector as a shared borrow and a mutable borrow, which would introduce aliasing and mutation. And so you get an error. That's ruled out. Okay, so this is another kind of bug that Rust can catch for you. Another way of thinking about this is that when you have your hands on an ampersand mute value, that is the only active alias of the underlying memory at that point. Right? That's the only way to do anything. Just to spell this out a little more graphically, in an example like this, when we write ampersand vec in that let elem line, that introduces a borrow that lasts for the whole scope. So if we try to push later on in that scope, we get the same kind of error we got before in the previous example. That vector is borrowed. You can't mutate it, right? But once the scope ends, the loan is complete, and then you can go on and push on the vector. Right, so there's this kind of stack discipline to borrowing and this fine-grained tracking of which values have been borrowed that lets Rust catch these kinds of bugs. Okay, so that's the end of the basic ownership and borrowing story. I'm going to talk about concurrency next, but before I switch topics, I just want to make sure this part was clear. Yeah?
So I assume the compiler can do optimizations around a borrow, knowing that a non-mutable borrow, I should say, knowing that it can't be changed. So it might actually improve the code, or might find in other places.
Absolutely, and that's something we're not taking as much advantage of right now as we could, because we just use the LLVM toolchain, and it doesn't know this stuff. So we can communicate some of it, but I think there's a lot of avenue for actually getting faster than C++ this way, because you know so much more. Any other questions, comments before we move on? Okay, so now I want to switch gears and talk about concurrency, which is another enormous source of bugs that a lot of recent languages are targeting in various ways. And this is, I'm going to sort of go through a litany of different kinds of approaches to concurrency and the way that you can model them in Rust and how they help you catch bugs. So let me start with one particularly pernicious bug that comes up in concurrency, which is the notion of a data race. So a data race is defined as having two threads that are accessing a piece of memory where at least one of the threads is doing a write, and those accesses are not synchronized in some way. What synchronized means here is actually quite flexible. There are just simple reads and writes where you just say to the compiler, this is considered synchronized, and that has certain implications about optimizations. So I don't necessarily mean locks or something like that. It could be much lower level. But this goes back to what I mentioned before. If you have a data race in a C or C++ program, the compiler can do anything. Basically, your program has no meaning if you have this kind of bug. Because the optimizer can sort of break your code arbitrarily. But this kind of bug is very, very, very easy to create by accident. Okay, and it can, because of that undefined behavior aspect, basically this is as problematic for safety as the dangling pointer problems that we were seeing before. So if you want a safe language, you just can't allow data races at all. So the ingredients of data races basically come down to aliasing, because you have to have two threads, mutation, because at least one has to be writing, and then no ordering, which is another way of saying lack of synchronization. And of course, those first two bullets are familiar from what we've seen so far with the ownership and borrowing. So you might expect that we could sort of reuse some of the tools that we've seen already, and that turns out actually to be the case. Right, so I sort of mentioned that there are a lot of languages trying to tackle concurrency bugs in various ways, and many of them propose specific models of concurrency. So there's the actor model, which is espoused by languages like Erlang, for example. And there, in principle, you're forbidding aliasing, so you're passing around owned values between different actors. And on the other hand, there are functional languages like Haskell, which let you alias all you want, but disallow mutation. And Rust's approach is sort of all of the above in the sense that you can do either of these. You can, as we saw, with different kinds of references, you could allow or disallow mutation or aliasing and do so at different times. Okay, so that leads to sort of many different concurrency models that you can build up in Rust. And all of this is done in Rust libraries. It's not built into the language in any way. Okay, so let me start with a really simple discipline, which is basically the actor model. Yeah?
That's disturbing. Why is that built into the language at some level?
Because why is it not built into the language? So I actually take this.
It says that your implementation takes all of the concurrency from the very low level of the machine and pushes it up a level or two so that you can do things underneath between Rust and the machine to accomplish magic.
Right.
That doesn't seem to be the right thing to do.
So it's pretty interesting. When Rust started, it was taking a very different approach where concurrency was baked very deeply into the language, and it sort of followed the actor model. But over time, what we realized was that these kinds of disciplines of concurrency actually just fall out of the ownership system. That is, and I'm going to show you what that looks like. But basically, you can build in a library something that gives you the guarantees you want. But by making it a library and rather than the language, it's open-ended. Anyone can build new libraries. You can keep adding new concurrency constructs without actually changing the whole language, right? So I think it's actually a huge benefit.
Just to add on what Dennis was going to say,
yeah.
I was getting ready to ask you a question about message passing and the like. need this time to write a slide. But Mr. Acker will be speaker otherwise, so he's not throwing snowballs at you.
Okay, good. I'm safe.
Carl's not here.
Cool. Okay. Well, I mean, one of the things I want to say is that Rust can do the actor model very nicely, and in the following way. So now I'm going to sort of go back to stick figures for a moment and think about these stick figures, instead of being different functions that are calling each other, different threads that are communicating, right? And so in the actor model, a thread has ownership of some data, and that becomes a message that's passed to another thread. And that message passing is supposed to designate ownership transfer, right? And then that other thread might form some other message and transfer ownership back over. And the key thing is that because it's ownership, there can't be aliases, so all communication between threads has to go through this message passing. Okay, going from stick figures to code, here's what this actually looks like in Rust. And I'll go through this fairly quickly, but so we first of all set up a channel, and a channel has two ends, a transmission end and a receive end in Rust, at least in the particular library we offer. And that looks like sort of this diagram in terms of the memory layout. So those two ends are sitting there on the stack, and then they point to some data on the heap. The actual data is not so important. Then we spawn some child thread. Okay. And this double pipe syntax, don't worry about it too much. It's basically expands out to, we have some piece of code. We're writing a function, just an anonymous function, that is going to be the body of the child thread we want to run. Okay. And notice that in that child thread, we're mentioning the transmission side. Okay. And there's also this funny keyword move going on, right? So there's a lot going on here, but the point is, by writing move and mentioning the transmission side, we're saying this child thread is going to take ownership of the transmission side of the channel. Okay, so after the spawn, the parent thread is not going to be allowed to use tx anymore, just as if it had been passed in a function. Okay, and then when the child thread executes, it allocates a new vector. It does some stuff with that vector, maybe pushes some data into it, and then at some point it sends that vector back across the channel. Now this send only involves the stack data, basically, just like every other ownership transfer we've seen, which is fairly small, right? That's just a few words of data that's being transferred from one thread to the other. The bulk of the data, which is sitting in the heap, didn't move at all, right? And that way, you're passing pointers back and forth between threads, but you're getting a lot of help from the language to make sure that nothing goes wrong in terms of dangling pointers or aliasing a mutation, like I've shown you. But this is all just using the existing ownership discipline. Not even any borrowing. It's just pure ownership to transfer these between threads. Is that fairly clear? Getting some.
Well, it seems to me that there are two issues here. On the one hand, you have the physical representation, the data structure. Mm-hmm. And on the other hand, you have the abstract information, which may be passed along or copied or moved or mutated and then put back into a data structure.
Yes.
And does the language differentiate strongly between that? Or is it basically really talking about the representation of the data in memory and deals more with the physical layout of that data and its addresses?
Right. Okay. Yeah. So basically, okay. So the question is essentially, there's potentially a distinction between ownership transfer in some abstract sense and the actual physical layout that's involved, and how does that look to the language? So by default, the language unifies the two, essentially. Like when you write a data type, there's a sort of, you're assuming everything in it is owned. And so if you pass it along, you're passing that stack representation. But there are various ways to say to the language that you want some more abstract notion of ownership. And when you do that, that generally involves breaking out of the ownership system in some way. And I'm going to talk about that escape hatch bit at the end. But so you have the flexibility to do that, and that's very important.
Is there anything equivalent to a promise?
Yes, there is. Yes, and that's also built up as a library. Okay. Here's another another example of concurrency. So we saw the actor model. Here we're seeing the sort of pure functional model where we're just passing some data to a bunch of threads so that they can read from it. Right? This is a really simple model for concurrency. And in this case, the thing is, we have a bunch of threads that all have access to a vector, and it may not be clear at what point they're done with the vector in some sense, right? There may not be any single thread that clearly owns the vector or is going to outlive the rest. And so there's this notion of ARC, which stands for atomic reference count, which is a smart pointer if you know C++. So it's a kind of pointer that does some interesting stuff when you work with it. And basically, it's just maintaining a reference count, how many threads are actively looking at this object. And when the last thread destroys its arc, basically, then the vector itself is destroyed. So in some sense, the arc itself owns the vector. That's one way of thinking about this. But then, again, you can reason about the layout. Inside the arc, you have the vector just laid out directly, exactly as we saw before. And because that is stored inside the arc, there are no aliases to the vector itself. Everything has to go through the arc. In particular, the arc only allows you to get out a shared reference to the vector, as you'd expect, because the whole point is to allow aliasing between different threads. Okay, so that's pretty simple. There's kind of an interesting aspect to this, though. So going back for a second to send, like you might use with a channel, the library is set up so that when you're sending a type, that type has to be marked send. What does send mean? Basically, it means thread safe. Okay, in particular, there are two forms of reference counting that are commonly used in practice. There's atomic reference counting, which uses synchronized accesses to change the reference count. And then there's sort of non-atomic reference counting, which is much faster, but it's not safe for use concurrently. So the key thing is that those two types are marked send and not send, respectively. And therefore, you know if you're using the non-atomic version, there's no chance that it will ever migrate to another thread and create a thread safety problem. So Rust is actually checking that when you pass data between threads, that data is actually thread safe to use, right? And that rules out another class of concurrency bugs. Okay. Let's look at a few other concurrency models. So, of course, we have to talk about locks. Rust can do locks, and it has a sort of interesting story there as well. So with locks, right, normally you just have some type mutex that represents a lock, and you have the ability to acquire the lock or release it at some point. But in Rust, the mutex type actually takes another type as an argument. And that other type represents the data that the lock protects. And so what's kind of interesting about this is the mutex never gives you direct ownership or access to that data. Instead, it gives you a kind of what's known as a guard in C++. So it's a value that points to the data, but doesn't give you full ownership. And this is a bit subtle, but you'll notice that in this function call, I have a lock, and I don't say unlock, which might seem strange. But actually, what's going on is that the guard that I get back when I ask for a lock will do the unlock when it's destroyed. So I get back this value, this value data. I can use data to mutate or otherwise access the data protected by the lock. And in fact, that's the only way I have of getting to that data. And the only way I have of releasing the lock is by destroying my guard data. Okay? And so if you put this all together, what this means is there's no way to access data that's supposed to be protected by the lock when you don't own the lock, right? When you're not actually in a critical section, ruling out yet another classic class of concurrency bugs. Okay, that's maybe a little subtle to see, but hopefully the gist is clear. Yeah.
To log the mutex doesn't have to be mutable.
Yes, and that's right. So this is a place where the rules are being bent slightly, because obviously locking the mutex does involve mutation under the hood. But you don't want to require a mutable borrow of the mutex because then only one thread could own the mutex, right? The whole point of a mutex is to allow aliasing across threads. So actually what's going on here is very interesting because, like I just said, part of the reason to have a mutex at all is that you want lots of aliases to some data and for those aliases to be usable for mutation, which sounds like a problem from what I've been telling you. But the other aspect of the mutex is mutual exclusion. So a mutex is ensuring at runtime that you never have multiple threads mutating at the same time, right? And so the overall discipline is still followed. It's just being performed sort of dynamically through the synchronization of the mutex rather than completely at compile time. Okay, but that's, again, just built up as a library. Does that make sense? There's a lot going on here. It's a little hard to get, but.
So you're using mutex to protect the block of code, but that's a synchronization mechanism, rather simple-minded. And you provide others as well.
Absolutely. And because this is all built as a library, it's sort of completely open-ended what synchronization mechanisms you build. But we have lock-free data structures, for example, and many other forms of more sophisticated, like barriers, semaphores, all kinds of stuff. Okay. Now I want to give one last example, switching gears from focusing on concurrency and concurrency bugs to parallelism, which is closely related, but not exactly the same thing. All right, so a classic example of an algorithm you might want to parallelize is something like quicksort, right? A divide and conquer style algorithm. So here's sequential quicksort written in Rust, where we're given access to what's called a slice. So I guess I haven't introduced this notation at the top where it says vec and has these bars, but basically, or the square brackets. You can think of that as a sort of fixed size window into a vector. So it's not the whole vector, it's just a window into it. And that's kind of key for what's going on here. Because in particular, right, we start with this whole slice and we're gonna pick a pivot point. And then once we've done that, we're going to actually partition the slice into two independent slices. And there's a function in the library called split at mute. And what that's doing is it's saying you have a reference to some whole slice of a vector, a mutable reference, and you want to turn it into two mutable references to disjoint subslices, right? And so that's safe, even though they're both talking about the same underlying vector. Because they're disjoint, you can't actually get into any trouble by using these to mutate the underlying data, okay? And then we go on to actually do the sort. So that was the sequential version. We can do the same thing in the parallel version. Basically, the code looks almost exactly the same. So we do the partitioning. We get these two subslices. Only this time, we are actually sort of asking to do the recursive calls on some child threads, right, using this parallel join thing. Now, something very interesting is going on here because we have the parent thread, the initial call to parallel qsort, and we have two children threads which are actually being given pointers onto the parent thread stack, which is a very dangerous thing to do because those pointers must not outlive that stack frame or you're going to be in real trouble. This is yet another kind of bug that is very easy to make in C++. The key point is Rust only lets you do this if you're doing something like a join, right? And the type system can actually talk about whether you are accessing stack data or not. And in order to give out stack data to children threads, you have to be joining on those threads. And that's important because it prevents that stack frame from being popped while the children threads are running, right? You're waiting for the children threads to finish before you continue and pop the frame. Yes?
How can a library do that? That's a global check the compiler would have to make.
Sorry, which check do you mean about the stack?
You said that if you split, you must join.
Yes. So what happens is when all data in Rust has something called a lifetime associated with it, which I haven't talked about at all here, but it's sort of implicit. And that lifetime refers to the borrows that are active in that data. And there's a way of saying that the lifetime has to be static, which means there are no borrows inside. And that's a way of ruling out stack data, basically, or sort of pointers onto stack data. So in the libraries, what I'm saying is that there's one way to spawn a thread, just the spawn keyword or the spawn function that I showed you. That requires that the child thread have a static lifetime. Basically, that you're saying the data that's being passed cannot have any borrows into the stack. But then this join function can take any lifetime. So basically, the type system allows you to say whether stack data is allowed or not. And then the libraries themselves build different APIs where they're tying this together with things like joining. Does that help?
Not quite, but because there's nothing up there that implies it has to be static, unless it's a requirement of split and mute.
So in this case, it doesn't have to be static, right? That's the point. Because the join function is allowed to take non-static closures as an argument, precisely because you know that the semantics is it will join those two threads at the end, so the stack frame will be valid for their entire duration. But the spawn function that we saw before, that has a static constraint. And so if you tried to do this with spawn, you'd get a compiler error. Like if I just said spawn twice for the two children, that would not compile because of the type signature.
So the question is, how does join and spawn get the information that some portion of the data structure must be static?
So they get it by, so I haven't shown you their type signature, so I'm sort of like alluding to this thing that I don't have on a slide, unfortunately. But basically, if you were to put their type signatures side by side, spawn actually says static in part of its type for the closure, and join does not. And then, so then you're sort of hooking into the compiler, so the compiler knows whether stack data is involved or not, and this gives you a way to ask for it.
And that's built into the language and not into the...
That's right.
Into the library.
That's right. So the notion of lifetimes and static, that's a language feature. This is an example of the libraries taking advantage of it. Okay, I guess I should probably move on just to wrap up on time here. Okay, I sort of walked through there. So, okay, at this point, I'm basically going to just conclude the talk. So, I've shown you several different models of, typical models of concurrency, how you can support them in Rust, and the kind of strong guarantees that you get that rule out classic bugs for each kind of model. But as I said, because this is all being done with the libraries, it's very open-ended, and it's under very active development. So, futures or promises are one thing we have some, small support for, but we want to do a lot more. And I mean, this is just an endless list. But one key point is that all of these sort of approaches to concurrency, and when you build them in Rust, are data race free by construction. Okay, and now I sort of pull back the curtain, right? So I've been sort of alluding to this all throughout the talk, that the discipline can be too strict. You need to bend the rules in certain ways, right? Which should make you uncomfortable. It certainly makes me uncomfortable. So one of the key things that makes Rust work, or sort of workable, is the notion of unsafe code. So there's a keyword in Rust called unsafe, and basically within an unsafe block, you are allowed to break certain rules that are normally in play. Which may sound like you're just throwing all of these great guarantees I mentioned out the window, right? I mean, that's the typical first response. Like, if you have this, what's the point? And from a sort of purely theoretical point of view, that's totally true. As soon as you have one unsafe, there are no guarantees. But the key is, in practice, you actually need unsafe relatively rarely, usually in data structure libraries or like concurrency libraries, and you can use it in a constrained way. And in particular, you can hide uses of it behind an abstraction boundary, so that you can say, if you build a mutex, for example, under the hood, that uses unsafe. That breaks the rules in certain ways. But it guarantees at the public API level, the things you can actually do with a mutex are perfectly safe. And in fact, every use of unsafe has to make that guarantee. It has to be hidden behind a boundary so that users of that library get all the guarantees of Rust back. So it's encapsulation of safety. Yeah.
How do you prove that?
So that is proved on the side, right? So this is not something this is not something that the compiler, at least today, can give you help with, right? But you can search for uses of unsafe in your code, right? You can find the places where you might be breaking the rules, and there's a strong sort of culture in Rust and its ecosystem to avoid unsafe whenever possible, right? So it's much easier to audit your code, and actually there is ongoing work in academia to try to go push this further and actually understand what it would take to prove unsafe abstractions safe, right? And maybe build some additional tools to help you do that.
Limiting the potential pain. Yeah.
Yeah, I mean that's exactly it. Like, at the end of the day, if this is going to work, it has to be practical, and you can't have a completely rigid set of rules like the ones I showed you and scale all the way up to a web browser. But our experience so far says you can get a really long way using unsafe quite minimally.
You really only need one unsafe.
Yeah, that's right.
Put it all in the same bucket.
That's absolutely right.
Total outer parentheses.
Yeah, exactly. So, okay, and then just sort of information about where Rust is right now. So we are deeply in the midst of a sort of final push toward a 1.0 release. So at the end of this month, we'll put out a beta, and then 6 weeks later, we'll put out the actual 1.0 final. And one of the things, up to this point, we've been breaking code on a daily basis. So it's been very hard for people to use Rust in a production way. But that's going to change with 1.0. So this is the point where it switches from research project to something real that people can build on. So obviously, I'm very excited about that. Great. Well, I think I'll just leave these conclusions up here and take any final questions. We do. You should download it and try it out. So it segfaults very rarely. Yeah, so we have servo runs. You can browse the Rust GitHub repository on servo. You can actually do quite a bit. It runs on phones. And in fact, this year, one of our goals is to have a component, a module of code that's shared between the servo browser and also Firefox. So we're sort of trying all avenues for getting Rust actually in use in the organization. I think once we're shipping one module, then they're stuck with it. Then Mozilla has to deal with Rust forever. That's our secret hope. So. Yeah.
What do you think is the biggest challenge moving forward? What keeps you up at night?
Oh man, what doesn't? So that's a really interesting question. I worry that, yeah, well, you said besides the unsafe, but I mean, whether this vision about unsafe being constrained enough will actually succeed is one thing that keeps me up at night. And the fact that right now, to program even a simple data structure like a doubly linked list that involves aliasing and mutation requires a little bit of unsafe code. That worries me, but I think we have a lot of ideas for how to push the boundary farther to give you building blocks that are safe that you can use to build things like linked lists. But I don't know. I mean, we're sort of doing the best we can to, make all these promises. Like I said, we're not going to break any code after 1.0. And so the other thing that keeps me awake at night is like, what if we made some of those decisions wrong and we haven't had enough time for feedback?
There are lots of digits after the 0 point.
Yes. Yes, indeed.
So what's your competition?
That's an interesting question. There aren't a lot of languages that are targeting this combination of safety and control. In a way, I think we're the only game in town there. Certainly, most other languages that are trying to give you that level of control at least require a garbage collector. But I think Rust is often compared to Go, in part because Go is also by a company that makes a web browser and it's a recent language. People are sort of looking for a new thing. I think Go and Rust are targeting pretty different niches, honestly. So I mean, C++, actually, if I was to be honest, I think C++ is the biggest competitor to Rust. And part of the reason I say that is Rust, well, C++ has come a really long way. And a lot of the ownership stuff I'm showing you in Rust resembles what it's like to write C++ code these days. It's just that C++ doesn't actually check it for you. And a lot of it is done at runtime, right? And there's a lot of cruft in C++. It's an old language, right? But I think that's the biggest risk, is that C++ might get good enough that Rust just never has a chance to take off.
What's going to happen when the programming model changes and some of the stuff that's being experimented with, where you move memory referencing and the MMU up into the low-level code and try to do memory synchronized accesses, that sort of thing? How's that going to fit into the Rust framework?
So that's an interesting question. I think that there are sort of two answers to that. One is a theoretical answer and one is a practical answer. So in theory, the core discipline of ownership and borrowing, I think, is very widely applicable to many different architectures and styles of programming. So I think, even if, cache coherence goes out the window, for example, I think that ownership will still be an important aspect of programming and something that the type system can offer you. On the other hand, practically, we're very tied to LLVM right now. And who knows how long that will last. Hopefully someday there will be a Rust standard and many Rust implementations, but that's a long way off. Yeah.
I don't think you said so, but I'm assuming that in Rust you can't manipulate pointers in the sense of incrementing them.
It's not the pointers I showed you. There is a kind of unsafe pointer that you can only manipulate in unsafe code, but that's used very rarely.
It's an unsafe only feature.
Exactly. Yeah.
What's with the name?
It's oxidized iron.
Look it up online.
Okay.
Anybody else?
Well, so have you thought about writing an OS in this?
People have. Hobbyists have. Nothing too serious. But that's definitely something you could imagine doing. There's a lot of work needed to, right now, Rust works relatively smoothly because you can assume an allocator, and the libraries are sort of shaped around that. And for an OS, things are a little bit different. So I think the standard library would have to change quite a bit to write a serious OS. But there are lots of hobby projects doing it already.
Is it easy to link it to existing C library or maybe C++?
So it's very easy to link it to C libraries, and that actually drove a lot of the recent design. So that, in comparison to Go, for example, it's much easier. Rust just looks like C. C++, the story is not as good, except that C and C++ are relatively easy to interface together. So you at least have that starting point. But Rust doesn't have anything like classes right now. It has other features that give you parts of what classes do. So that story will evolve over time, I think.
Anybody else?
Well,
You get the close.
it's essentially a social comment. Essentially explanation why I said limiting damage. I have to go back to my grandfather. He used to borrow tools. But he had this very strict rule. Whenever you turn your tool, you bring it back in the same state or better. No damage, in other words. And I accept that. It's sort of obvious, right? It's courtesy. And when I came, I'm born in Switzerland. When I came to the US, this young lady, professor in mechanical engineering, had this thing about designing bikes. Mm-hmm. And I was very pleased. The first rule she had, well, you're getting these old bikes and you have to return them at the end of the course in a better state. Bingo. Well, unfortunately, she didn't adhere to that, but that's not the main point. It's a social thing, basically. I accepted the way I grew up. She sort of thought it was cute. I mean, in the US or California, different rules, right? And she abandoned it. And yeah, that's what you pay for. That's why our systems are unsafe. If you would sort of borrow nicely, right?
Right.
Then you wouldn't have a problem.
Right.
So anyway,
Yeah.
I just shocked in some sense. That's why I asked probing questions to you, because I knew where I wanted to go with that. And you gave me the answers. Yes, keeping it simple.
Excellent. Yeah.
So
Well,
I'm glad you discovered it.
Thank you very much.
Thank you all.